Does Jordan's ghost haunt x prime equals ax when A is defective? Now, of course, Jordan is Camille Jordan, after whom the Jordan form of a matrix is named. And by way of apology for the title, what I'm really asking is, to what extent does Jordan form theory lurk behind the process of solving linear systems when the matrix is defective? Can the linear system with a defective matrix be solved without Jordan's ghost hovering over the problem and clanking chains and scary noises? Oh, yeah. What's a defective matrix? It's one that does not have a full set of eigenvectors. In other words, the geometric multiplicity of an eigenvalue is less than the algebraic multiplicity. So the set of eigenvectors has to be augmented with generalized eigenvectors. So our goal here is to use some examples, generate some solutions of the differential equation x prime equals ax, but a is defective. So here is this naive approach that you'll find in most books, and they start at the bottom of the chain. They start with the eigenvector, the known eigenvector. It gives a first solution to the differential equation. To get a second solution in the defective case, it requires getting a generalized eigenvector, and a third solution requires getting another generalized eigenvector, working up the chain from known to unknown. So the first generalized eigenvector would be a solution of this equation. This is the unknown, this is the known. Solve this system for this vector. To get another one, you would solve this system. This is now known. This would be the unknown. Solve this system. So that's going up the chain starting from the eigenvector. If that's sufficient, then you don't need Jordan form theory, and the ghost of Camille Jordan doesn't haunt the process. So, what would you need to know from Jordan form theory if you were tackling this problem with a little bit more insight? You would form the matrix A minus lambda I, and then you would look at powers of that matrix. Then you would get the null spaces of those powers, and you would discover that the null spaces are um, supersets of each other as you go up the chain. So this is the eigenspace. It is a subspace, proper subspace of this next null space, which is a proper subspace of the next null space. You go to the top of the chain this time. At the top of the chain, you find a vector that is in this highest null space, but not in the one below. And that's a tricky thing. You look in books and see how it's always a guess and gosh kind of thing. There's no recipe given for how to find that particular vector. Then you just take a product. C times that vector gives you the generalized eigenvector one below the step down the chain. You hit it with C again, and you get down to, in this case, you would get down to the eigenvector. Those vectors, if put into as columns of a matrix Q, it would turn out to be the transition matrix that would take A to Jordan form in a similarity transform. I've got three examples here. Let's look at the first one. Matrix. Eigenvalue 2, algebraic multiplicity 4, geometric multiplicity 1. You need three generalized eigenvectors. The eigenvector that you have, I've written as V1. This is the matrix A minus lambda I. When lambda is a number, you can forget about you don't need to put in an I. Maybe we'll subtract 2 from the main diagonal. So this is going up the ladder, naive approach. You want to solve a minus lambda I v2 equals v1. Well, linear solve is appropriate tool. You get a free parameter. I have chosen it to be 0. I've called the resulting vector v2. Can you go up the ladder one more step from v2? You do the same thing. Use linear solve, free parameter. I've chosen the free parameter to be 0. Yeah, the vector I get is v3. Can we go up once more? Same trick. I've chosen the free parameter to be 0. Call that resulting vector v4. Do I get 4 solutions out of this process? Here's the first solution, e to the 2t v1. Then you have e to the 2t, and you have this combination. Here's the first generalized eigenvector, t times the eigenvector itself. Once more, you've got the generalized eigenvector v3, e to the 2t, v3, t, v2, t squared over 2, v1, and the pattern continues with y4. Are these vectors linearly independent? Form a matrix, take the determinant. The determinant is non-zero. Are these solutions of the differential equation? Well, put them into y prime minus ay. I get 0, I get 0, I get 0, I get 0. What would Jordan form add to this particular discussion? Characteristic polynomial, power is 4. Minimal polynomial, power is 4. This tells you that you have a chain of length 4. One chain of length 4. Here are the null spaces. Null space of c, c squared, c cubed, c4. Here's a picture. The null spaces are nested. Here is M1, the eigenspace. M2 sits around it. M3 sits around that. M4 sits around that. What happens if you start at the top of the chain? You want to get a vector in the whole space that is not in C3. Here's a recipe for that. You don't see this in very many books. This is my recipe for doing that. Project a general vector in this null space, M4, and then get onto this null space and get the orthogonal complement. So here is a general vector in this null space, M4. This is projection. I use a projection matrix command in Maple. I'm projecting onto the null space here, this null space. Orthogonal complement. You have parameters because you've picked A, B, C, D here. If you make some of them 0 and you take a nice, here, take A is 51, you get this vector. Call it B4. Is that the top of the chain? Can you come down the chain from B4? So you define B3 to be C times B4. B2 is C times B3. B1 is C times B2. Are they the right vectors? Well, if you put them in a matrix, it will be the transition matrix from A to its Jordan form that tells you you've got generalized eigenvectors, and if you've got generalized eigenvectors, you can write down solutions to the differential equation. So in this instance, the naive approach worked. It's not too bad if you've got a tool like Maple to do some of this linear algebra. It's not too bad at all. If you want to understand better what really took place, a little Jordan form theory is helpful but not necessary. But now let's look at this second example. 3 by 3 matrix. Algebraic multiplicity 3, geometric multiplicity 2. So the eigenspace is, as mentioned, 2. There are 2 eigenvectors. Here's the matrix C, A minus lambda I. You try to go up the chain from V1. It doesn't work. This linear solve technique says you got inconsistent equations. You try to go up the chain from V2. It doesn't work. What do? Well, you scratch your head and maybe you realize that you need a special eigenvector in the eigenspace to go up the ladder from. So you try to find out what that special vector is. You take a linear combination, you make an augmented matrix, pivot to see what conditions on A and B have to be satisfied in order for the system to be consistent. Well, you pull out those two expressions, you find out it's really only one. You hit it with solve. You discover that A has to be 3b. You put A equals 3b. You get this vector. You let B be 1/7, and you get the vector 1, 2, 3. So this vector U is an eigenvector, but it's a special eigenvector. It's the one that allows you to go up the chain. So linear solve C U. You have a free vector. I've chosen a free parameter. I've chosen that to be 0, you get this vector, call it W. So W is up the chain 1. Do you get 3 solutions? E to the t v1, that works. But e to the t u has to be the second solution, and W is your generalized eigenvector, giving you the third solution. Are they 3 solutions? Yes, they are. Here I plugged into the differential equation. Are they independent? Yes, they are. Draw a picture. This gray thing is the eigenspace, two-dimensional eigenspace. The black and the red vector are v1 and v2. What is this blue vector? This is u. This is the 1, 2, 3. It's that special member of the eigenspace that allows you to go up the chain to that green vector. That green vector is W. It is the vector at the top of the chain in the biggest null space that is not in the next lower null space. Now, does that make sense to a student who only knows this naive approach? Is it easy for the student to do all these calculations? I'll leave that to you to decide. But if there was some Jordan form theory in hand, what would you learn? Characteristic polynomial, power 3, minimal polynomial 2. This tells you there is one chain of length 2. And you only need to go one chain of length 2, and you've got what you need. So you look at these null spaces, two-dimensional. This null space is three-dimensional, it's the full space. You need a vector in the full space that is not in this null space, the eigenspace one below. A simple way to get a vector in this case, take the cross product of v1 and v2. It will be orthogonal to the eigenspace. Let that be the vector at the top of the chain and work down from that vector. See, call it B, C times N, it's B. Are those vectors appropriate? Will they do the job? Well, if you make a transition matrix with those as the columns of the matrix, it's a transition matrix, puts you in Jordan form, so you know you've got the appropriate tools to to get 3 solutions to the differential equation. Now, I think I have time to look at this third example. It's again a case where the matrix A is defective. Algebraic multiplicity 4, geometric multiplicity 2. Here are 2 eigenvectors, V and W. A minus lambda I, call that matrix C. You cannot go up the scale on either V or W. So you try the linear combination trick. You have to pivot, but then you got to pivot again. Imagine doing that with a pencil and paper. Here are the conditions on the linear combination coefficients A and B. You discover that A has to be minus 2B. You do that, you get a vector N. Can you go up the ladder from N? Well, linear solve takes you to this vector. Keep all of these coefficients because you don't know what you're doing here. So you get a vector M. Now, can you go up the ladder from M to get that fourth vector? No, doesn't work. Inconsistent system. So you form an augmented matrix, you pivot again. Look at all the algebra you would have to do by hand. Here are your two conditions. Turns out that S4 has to be this expression. Put that into M, get a vector T. Can you go up the ladder from T? Get a vector R. Now, do you have enough vectors? You make a 4 by 4. Is that a transition matrix with those vectors? Yes, you could solve the linear system because you've got the appropriate number of generalized eigenvectors. Now, what would that look like if you took the Jordan approach? Characteristic polynomial 4, minimal polynomial 3. This tells you you have one chain of length 3. So you get your null spaces, two-dimensional here, three-dimensional here, the full space here. Use the projection trick to get a vector in the whole space that is not in this null space. That I distill down to vector B3, this one here, I'm going to jiggle these coefficients, come down the chain. C times B3 is B2, C times B2 is B1. Will they work? You make a matrix K. Is it a transition matrix to Jordan form? Yes, you can therefore solve the differential equation because you've got the appropriate vectors. Much simpler. This algebra is daunting. This pencil and paper would be daunting. If you have a tool like linear like Maple, you can do much more than this naive approach. You can learn some theory. You can see how Jordan form theory fits into the problem. We've got about a minute and a half left. Very quickly, this section has a number of places where people have tried to avoid Jordan form. And here is a final piece of irony. At Rose-Hulman, one of the engineers that I got to know well, claimed in the real world there are no defective matrices. So we're teaching students stuff that they never really need. Because in the real world, matrices are populated with floats that are imprecise. So I asked myself, does it really matter? And I did this little experiment. Differential equation, this coefficient 1.01, and here I've made exactly 1. Here the solution comes out to be exponentials times trig. Here the solution is exponential times polynomial. What is the difference in norm? Very small. And if you draw a picture of these two, red and black, one on top of the other. So you pay your money and you take your pick. Does this stuff matter? Do we really need to be teaching our students this stuff about defective matrices? And if we decide that we have to teach that stuff, then how are we going to teach it? Are we going to teach it from a naive perspective, or are we going to go full bore and show how Jordan form theory enlightens the process?